All right, so let's get started here on 1.3. And so what we're going to start with is talking about how we measure angles. Again, should be stuff you are familiar with, but quick review of it. The main thing we want to measure with is radians rather than degrees. We can do it in degrees or radians, but radians have a lot of advantage over degrees. They're kind of naturally based and kind of just appear for us, whereas degrees are kind of arbitrary and made up, and they don't work as nicely, as you'll see. So the number of radians in the central angle ACB within the circle, within a circle of radius r is defined as the number of radius units contained in the arc S subtended by that central angle. So if we have if we're looking at this picture right over here, we have some radius r, we have 1 radian, this is the length r, and basically what we're doing is ultimately the idea is we have a unit circle. Okay, we have a unit circle right there. And if we use that unit circle, its radius equals 1. And all other circles are similar circles, so any other circle we have is just going to be a proportional version of the unit circle. And if I look at a unit circle, I know that the circumference of a circle is 2 pi r. Well, if I'm on a unit circle, that r is 1, and the entire distance around the circle is just 2 pi. And so what we can do is just take fractions of that distance around the circle, around the unit circle, and use that as our angle measurement, and we can simply extend that out, extend it out to larger or extend it inward to smaller circles, and we can end up using that as a way to tell how far around the circle we have actually gone, that value being called S, which I'll highlight in yellow, and then theta is the angle on the unit circle, which we'll also use to indicate our angle on the larger circle, and then finally we have that radius r. And so how do we relate these things together? Well, the idea is that basically how many radii are in the arc S right there. How many are in there? How many radii are in the arc S? And we can do that with this equation right here. S equals r theta. This only works if you're in radians. This equation does not work if you are in degrees. So make sure you're in radians. And if we do that, this will also tell us that theta equals S over r, and we can see then that as we increase r, S is going to increase proportionally. So if I come up here and I draw a circle, like say, this was our radius here, and I come here and I make double the radius, and I draw a circle in with double the radius. See if it makes a nice circle there for me. Yeah, it did. If I do that, and I extend these lines out further, right, then what's going to happen is this little arc length right here, this one on the larger circle is, oops, forgot to turn that off. Turn off. Why isn't that turning off? Turn off. Sorry, there we go. I got it. This arc length up here, S, is actually going to be 2s. It's going to be twice the length of that one if the radius is twice as much. If the radius was 3 times as much, it'd be 3 times as much. If it was 1.5 times as much, then that little length that would get traced out there would be 1.5 times as much. So it's all proportional, which means we can use these unit circle radians to do all the other circles of different sizes. All right, next. How do we relate these radians to degrees? Well, the easiest way to think of it is that halfway, really, all the way around a circle is 360 degrees, and all the way around a circle in radians is just 2 pi. We just saw that on the other side where the circumference of the unit circle is just 2 pi. And so those two things equal each other, which gives us the most commonly remembered one, which is divide both of those in half, basically reduce it, divide both sides by 2, and it's 180 degrees equals pi. How to put radians there. Radians isn't really a unit, but we'll write it like one for now. You can kind of throw it away whenever you don't need it anymore because it's basically a ratio, so it's kind of dimensionless. So it's 180 degrees equals pi radians, which then leads us also to figuring out that 180 degrees over pi is, over pi radians is, sorry, hold on, I'm doing the wrong thing there. Put the radian in the wrong way. 180 degrees over pi is 1 radian. And we can also do that pi over 180, pi radians over 180s is just 1 degree. So these bottom two will be helpful, or really any of them are helpful in unit conversion. But this is the one you most often have to remember. And once you know what two values are equal to each other, you can use them to do some unit conversion. So anyway, let's try this next example here. We have a circle of radius 10 meters, so that's r. How long is an arc that subtends a central angle of 4 pi over 5 radians? So this here will be our angle theta. So for part A, we need to do S equals r theta, and r in this case is 10 meters given to us. Theta is 4 pi over 5 radians. Now again, we can just kind of throw out the radians at this point because we want a length, and we're going to end up with just meters as our units. And so 10 times 4 is 40. So this is 40 pi over 5 meters, and 40 divided by 5 is 8 pi meters. So that's the arc length that you would have walked around the circle had you actually walked around that circle. So if you had the circle like this, and you would have started here, and you would have walked around to wherever 4 pi over 5 is, something like right here. This would have been the 4 pi over 5, and then the length, the distance you would have walked around the circle, this top arc here, would be 8 pi meters long, okay? And that's where you would have ended up walking that length. Now for part B, they give it to us in, they give us theta, but it's in degrees. So we have theta equals 110 degrees. So the key to this one is if we want to use that equation, we have to actually convert it. And so we convert it by multiplying by, we put what we want to end up with on the top, which is pi radians, right? Getting this from right here, over what we want to get rid of, which is degrees, 180 degrees. That's this 180 degrees right there, okay? And if we do that, we get this, which, if you notice, equals 1. That's this right here, right? It equals 1. The degrees will cancel with the degrees, and we'll end up with, getting our angle that we want. So you need to do this multiplication and figure this out. I'll finish this problem in the notes for you afterwards, but give it a try, finish it up, find what the arc length is around the rest of the circle. Next page, I went ahead and kind of filled this out a little bit. It's a unit circle, but here's the unit circle in degrees. I'll post another video for you that has the unit circle fully filled out, all in degrees and radians and all the coordinates and everything like that. But here's a little preview of it, just with the degrees around to kind of simplify that part for you. Here, how do we draw these rays, initial and terminal rays for these angles? So basically these rays are just arrows. If we have an angle and the xy plane is said to be in standard position, if its vertex lies at the origin and its initial ray lies along the x-axis. So the vertex is simply the base of the arrow. See how it's an arrow? It's got an arrowhead at this end, and then the vertex is simply the base, the other part, and we put it right there at the origin. Now that's for the terminal ray because you can see it a little better, but for the initial ray, this would be the initial ray right here. We put its base right there, its vertex right at the origin, and then we're going to rotate it around to its final position from there. So we lie it along the positive x-axis, and then we rotate it around. So here, we're going to lie it along the positive x-axis, and then rotate it around to its final position called the terminal ray. Okay? That's what we are doing there. Now, you have to be careful with this because there is essentially an infinite number of ways to get an initial ray to end up at the same terminal ray. So if this is our terminal ray right here, This right here is our terminal ray. So in this picture, they're showing it, they're going around, they're skipping past it, and then rotating around more than once to get to it. We could have just done this little rotation right there, and we would end up at the same spot, okay? And we could have even done more rotations. You could have come into here and done, I don't know, you could have gone around a whole bunch of times and then eventually stopped right there. And so really, there's just however many times you're going around isn't going to matter as long as you end up in that same spot. We can actually have different angle measurements for the same terminal ray. So be careful about that. Here we're going around more than once. It's going around and rotating counterclockwise from the x-axis. That's the positive direction. Going over here, going counterclockwise here, or not counterclockwise, going clockwise here, sorry, is the negative direction. And that's just convention. And so here again, we're going in the negative direction again, but we're going around more than once and ending up there. So negative angle measurements are clockwise. Positive angle measurements, like this one right here, are counterclockwise. So just remember that's pretty much true in all your mathematics, that counterclockwise is considered positive and clockwise is considered a negative rotation. All right, also take note of this. From now on, we are going to assume everything's in radians unless it is otherwise stated. So if you get an angle measurement, assume it's radians, not degrees, unless it tells you specifically that it is degrees and not radians. All right, let's go through the trigonometric functions here. Here we've got the right triangle definition, and basically what we have here is, sorry, making sure the microphone was on. I recorded this whole thing before and didn't have the microphone on. So anyway, we have the sine of theta. Now what we have here is, this is our angle theta right over here. We have a side that's right next to it. That's called the adjacent side. We have a side across from it. That's called the opposite side. And then we have a side that's across from the, oops, why is it doing that? Oh, I laser pointed. That's across from the 90-degree side. That's the hypotenuse. So make sure you know this arrangement. Be careful. If you're given an angle up here, theta, then this would be the adjacent side, this would be the opposite side, but this would still be the hypotenuse because it's the longest side and it's across from the 90-degree side. So just be careful about where your angle is given. Sine, we can define as opposite over hypotenuse. Okay, you'll want to remember that. Cosine, we define as adjacent over hypotenuse. And tangent we can actually define as sine of theta over cosine of theta. And if you write in the opposites over the adjacents, so this is opposite over hypotenuse, this is adjacent over hypotenuse. What happens is these hypotenuses cancel, right? And I made it a little messy there, but the hypotenuses, they cancel, right? And so what we end up with is just tangent is opposite over adjacent, okay? Which still is sine over cosine. It's good to remember this right here. You're going to want to know that too. Cosecant is just a reciprocal of sine, which makes it hypotenuse over opposite, so just flip sine over. Secant is the reciprocal of cosine, so it's hypotenuse over adjacent. And then cotangent is just the reciprocal of tangent, so that's just adjacent over opposite. And then lastly, we have the circle definition. This allows us to extend everything else. We have that the sine of theta is y over r. Okay, sine of theta, right here, we got the circle definition here. And so what we can do is look at the x and y directions here and basically see that if we make a right triangle here, right triangle right there, we can use the above definitions to figure this out. This length here, this side over here is y, this side over here is the x coordinate, okay? And so that's x, that's y, and we can basically use the above definitions to figure this out. So let me erase that so it's not horribly messy. And so sine of theta is going to be opposite over hypotenuse. That's going to make it y, which is the opposite side from our angle, y over r. X is going to be the adjacent side, so x over r. Tangent is going to end up being y over x. Cosecant is the reciprocal of sine, so r over y. Secant is r over x, the reciprocal of cosine, and cotangent is x over y, the reciprocal of tangent. All right, so make sure you have that down and understand it pretty well. So I'm not interested in going into the cash rule. Basically, you just need to know when is everything positive. If you're up here, x is going to be positive and y is going to be positive. That's the first quadrant. In the second quadrant here, x is going to be negative, y is going to be positive. Okay? Over here, both x is negative and y is negative. And over here, x goes back to being positive and y stays negative. So as long as you can remember that about each one of these little quadrants and areas, you should be able to figure out then what each of the sine and cosine and everything are. So like for example, if I look at the sine value over here, well, sine value is y over r. All the r's, right, is y over r. All the r's are going to be positive. They're just a radius, all right? They don't have a positive or negative. But in that location, y is positive. So over here, my sine of theta would be positive. My cosine of theta here would be negative because the x is negative. All right, and cosine is x over r. Okay? And then you can do the same thing over here. Here they're both positive, so sine of theta is going to be positive. Cosine of theta is going to be positive, right? They're going to be positives. Maybe I'll put parentheses around them. Over here, cosine and sine are both negative, so sine is going to be negative. Sine of theta. Cosine of theta is going to be negative. Over here, cosine of theta is going to be back to being positive, and sine of theta is still going to be negative, okay? And then from there, you mix them together to make the other ones and pay attention to the signs, like, you know, if I'm looking in this here, tangent of theta, that's cosine, that's sine over cosine, that's a negative over positive, that's going to be negative. If I'm looking up here, tangent of theta is going to be a positive over a negative, sine over cosine, that's still going to be a negative. But if I look up here, tangent of theta is sine over cosine. Again, it's positive over positive, so it's going to be positive. If I'm looking down here, tangent of theta is sine over cosine. That's a negative over negative. That's also back to being a positive. So you should be able to figure out then the sign conventions for the other ones. And then, of course, the secant, cosecant, cotangent, they're just going to match up with their corresponding ones for sine. So like here, cosecant will also be positive. Whereas down here, cosecant would be negative. Okay? Little note on notation. If I have something like 3 times x over 3 times y, those 3's will cancel and I'll just have x over y. Because this is 3 times x and 3 times y, and therefore they are going to cancel out when we divide them, because division is the opposite of multiplication. Well, if I look over here, if I have something like cosine of x over cosine of y, this is not going to end up equaling x over y. I cannot just cancel out the cosines, because this is not cosine times x. It's cosine of x, all right? You're taking the cosine of x. You're not taking cosine times x and cosine times y. So we actually have to have an inverse operation for this, and we'll talk more about it later, but it's called the arc cosine. And if you take the arc cosine of the cosine, you'll end up getting 30, like 30 degrees like that. That is what undoes it, not this. Please note that this cosine to the negative 1 is not 1 over cosine. So cosine, this is not equal to this. Okay, so be careful of that. Those two things are not the same. All right, next here, concept evaluating trigonometric functions. So here, basic idea is if you know the unit circle, it can help you. So for example, if I'm looking at pi over 4 angle, then the coordinates there are square root of 2 over 2, square root of 2 over 2. And so I can just pick out, because this is the unit circle, the radius equals 1, I can just basically pick out the x and y values for these. So cosine of pi over 4, I just pick out the x value, square root of 2 over 2. Sine of pi over 4, square root of 2 over 2. I just pick out the y value that time. Happens to be the same for this one. That's a pi over 4. Tangent of pi over 4 is just going to be the x, or the y divided by the x, so that's just going to be 1 because they're the same. And then as far as the other ones go, like cosecant, right? I can just do cosecant of pi over 4 by just doing the reciprocal of square root of 2 over 2, which is 2 over square root of 2, which if you do it out just ends up being square root of 2. Okay? So let me separate that from this one. I'll show you a couple more sides here. Let's look at, let's look at these ones. This is going to be, this one is pi over 6. This one is pi over 3. And then let's do one way over here. Let's do, what is that? What is that, 4 pi over 3? So this all the way around here is 4 pi over 3. And the coordinates for these locations, this one is square root of 3 over 2, 1/2. This is 1/2 square root of 3 over 2. This one is negative 1/2 negative square root of 3 over 2, which I'm going to show you in the video for unit circle how to get all these coordinates like this. But then you can go through and you can do things like, what's the cosine of pi over 6? Well, I'm just going to pick out the x value from the pi over 6 coordinates. Square root of 3 over 2. What is the sine of pi over 3? Well, I'll just pick out the y value from the pi over 3 coordinates, which is, again, square root of 3 over 2. What is the tangent of 4 pi over 3? Well, that's going to be the y value, negative square root of 3 over 2, divided by the x value, negative 1/2. The negatives cancel. Square root of 3 over 2 divided by 1/2 is square root of 3 over 2 times 2, so the 2's will cancel, and you're ultimately left with just square root of 3. Okay? That's pretty much it for this video. The next video will just go over unit circle, and then I'll finish up the chapter in another video. All right, thank you.